Hello everyone. So we will be discussing about a guide on artificial recharge to groundwater. So coming to the artificial recharge to groundwater, the main aim is augmentation of groundwater or a groundwater reservoir by modifying the natural movement of the surface water. That too by utilizing some suitable civil construction techniques. Why do we focus on this artificial recharge? Because this artificial recharge is used to enhance the sustainable yield in areas where overdevelopment has depleted the aquifer, and also in the conservation and storage of excess surface water for future requirements, since these requirements often change with the season or a period. So we need this artificial recharge techniques, and this also is used to improve the quality of existing groundwater through dilution, and finally to remove bacteriological and other impurities from the sewage and wastewater, so that this water is suitable for reuse. So the basic purpose of this artificial recharge of groundwater is to restore the supplies from aquifers that are depleted due to excessive groundwater development. So coming to the groundwater or subsurface reservoirs, we will discuss a few things. The subsurface reservoirs are usually very attractive, and they are technically feasible alternatives for storing surplus monsoon runoff. The subsurface reservoirs can store substantial quantity of water. These subsurface geological formations may be considered as the warehouses for storing water that comes from the sources that are located on the land surfaces. Beside the suitable lithological conditions, other considerations for creating the subsurface storages are favorable for geological structures and physiographic units. The dimensions and shape of these geological structures and physiographic units will allow the retention of substantial volume of water in the porous and the permeable formations. So the subsurface reservoirs that are located in a suitable hydrogeological situations are generally environment friendly and economically viable propositions. The subsurface storages have advantages of being free from the adverse effects like inundation of larger surface areas, loss of cultivable land, displacement of local population, and substantial evaporation losses, and also the sensitivity to earthquakes. No gigantic structures are needed to store the water, because these are underground storage of water. So this will have a benefit in the influence of the existing groundwater regime. The deeper water levels in many parts of the country, either of natural occurrence or due to excessive groundwater development, may be substantially raised, resulting in the reduction in the lifting cost and energy saving. The quality of the natural groundwater would substantially improve in the brackish and the saline areas. The conduit function of these aquifers, thereby reducing the cost intensive surface water conveyance system. The effluents resulting from such subsurface storage at various stages and various surface intersection points in the form of a spring line or a stream emergence would enhance the river flow and improve the presently degraded ecosystem of a riverine tract, particularly in the outfall areas. The structures required for recharging groundwater reservoirs are of very small dimension and cost effective. They are like the check dams, the percolation tanks, surface spreading basins, some pits, subsurface dikes, etc. So, we will discuss about the basic requirements for artificial recharge products. That means, if you are planning for any artificial recharge techniques, then what you should have is availability of non-committed surplus monsoon runoff in space and time. That means that particular location should have more surface runoff during the monsoon seasons. And the second requirement is the identification of suitable hydrogeological environment and sites for creating subsurface reservoir through cost effective artificial recharge techniques. So, these are the two basic requirements for any artificial recharge works. Now, the next requirement will be source water availability. As we have discussed, this is the first requirement. You should have some water, then only you can recharge any pit or anything artificially. So, the availability of the source water is one of the prime requisite for groundwater recharge and is basically assessed in terms of non-committed surplus monsoon runoff, which as per present water resource development scenario is being unutilized. This component can be assessed by analyzing the monsoon rainfall pattern, its frequency, number of rainy days, maximum rainfall in a day, and its variation in space and time. The variations in the rainfall pattern in space and time and its relevance in relation to the scope for artificial recharge to subsurface reservoirs can be considered by assessing the surplus surface water availability. This is one thing. Next, we need to also understand the hydrogeological aspects. So, in the hydrogeological aspects, detailed knowledge of the geological and the hydrogeological features of an area is necessary for adequately selecting the site and the type of recharge structure that is planning to be done. In particular features, parameters and data to be considered are generally the geological boundaries, the hydraulic boundaries, inflow and outflow of waters, storage capacity, porosity, hydraulic conductivity, transmissivity, natural discharge of springs, water resources available for recharge, the natural recharge, again water balance, lithology, depth of aquifer, and tectonic boundaries. The aquifers best suited for artificial recharge are those aquifers which absorb large quantity of water and do not release them too quickly. Theoretically, this will imply that the vertical hydraulic conductivity is high while the horizontal hydraulic conductivity is moderate. These two conditions are not often encountered in nature. The evaluation of a storage potential of subsurface reservoirs is invariably based on the knowledge of dimensional data of the reservoir rocks, which includes their thickness and the lateral extent. The availability of subsurface storage spaces and its replenishment capacity further govern the extent of recharge. The hydrogeological situation in each area needs to be appraised with a view to assess the rechargeable capabilities of the underlying hydrogeological formations. The unsaturated thickness of rock formation that is occurring beyond 3 meters below the ground level should be considered to assess the requirement of water to build up the subsurface storage by saturating the entire thickness of the wadoos up to 3 meters below the ground level. So the upper 3 meters of the ground unsaturated zone is not considered for recharging, since it may cause adverse environmental impact like waterlogging, soil salinity, etc. The post monsoon depth to water level represents a situation of minimum thickness of water zone available for recharge, which can be considered surplus monsoon runoff in the area. The artificial recharge techniques will interrelate land integrate the source water to groundwater reservoir. Two effects are generated by the artificial recharge in the groundwater. They are a rise in the water level and increment in the total volume of groundwater reservoir. So now we will discuss about how to plan and design a artificial recharge source. First, we need to understand the identification of area. The artificial recharge products are site specific, and even the replication of the technique from similar areas are to be based on the local hydrogeological and hydrological environments. The first step in planning this type of project is to demarcate the area of recharge. The project can be implemented systematically in case of hydrological unit, like a watershed is taken for implementation. However, localized schemes are also taken to augment the groundwater reservoir. The artificial recharge of groundwater is normally taken in few areas. The areas are like where groundwater levels are declining on regular basis, and areas where substantial amount of aquifer has already been desaturated, and areas where availability of groundwater is inadequate in lean months, and areas where salinity ingress is taking place. So in the first part of the planning, we need to identify the area. Then we need to have some scientific inputs. The scientific inputs are like hydrometeorological studies. In this, these are taken generally to decipher the rainfall pattern, evaporation losses, and climatological features. These can bring out the extent of evaporation losses in post monsoon period, which would be helpful in designing the storages of any particular capacity with a view to have minimum evaporation losses. In semi-arid regions of India, evaporation losses are significant after January. Hence, the stored water should percolate to groundwater reservoir by this period. The data on the rainfall intensity, number of rain days, etc. help in deciding the capacity and design of the artificial recharge structures. And the second parameter in the artificial recharge project is hydrological studies. It is a basic prerequisite to ascertain the availability of source water for the purpose of recharging the groundwater and the reservoir. For determining the source water availability for artificial recharge, hydrological investigations are required to be carried out in the watershed or sub-basin or basin where the artificial recharge schemes are envisaged. Usually 4 types of source waters are available for artificial recharge. One is the in situ precipitation on the watershed. Second is the surface or canal supply from larger reservoirs located within the basin. Third is surface supplies through trans-basin water transfer. And finally, treated municipal and industrial wastewater. So the in situ precipitation will be available almost every location, but may or may not be adequate to cause the artificial recharge. But the runoff going unutilized outside the watershed or basin can be stored, transmitted to simple recharge structures at appropriate locations. In addition, one or both of the other two sources may be available in any situation. So few of the information is required for that. The quantity that may be diverted for artificial recharge, the time for which the source water will be available, the quality of source water and the pretreatment required, conveyance system required to bring the water to the recharge site. Hydrological studies are undertaken to work out surplus monsoon runoff which can be harnessed as source water or artificial recharge. So in the planning we have discussed about the hydrometeorological studies, hydrological studies. Now we will discuss about the soil infiltration studies. In case of artificial recharge through water spreading methods, soil and land use conditions which control the rate of infiltration and the downward percolation of water applied on the surface of the soil assumes special importance. Infiltration in its most narrow and precise sense can be defined as the process of water entering into a soil through the soil surface. Although a distinction is made between infiltration and percolation, the two phenomena are closely related since infiltration cannot continue unimpeded unless percolation removes infiltrated water from the subsurface soil. The soil is permitted by non-capillary channel through which gravity water flows downward towards the groundwater, following the path of least resistance. Capillary forces continuously divert gravity water into pore space so that the quantity of gravity water passing successively lowers the horizons and is steadily diminished. This leads to the increasing resistance to gravity flow in the subsurface layer and a decreasing rate of infiltration as a storm progresses. The rate of infiltration in the early phases of a storm is less if the capillary pores are filled from a previous storm. There is a maximum rate at which water can enter soil at a particular point under a given set of conditions. This rate is called as infiltration capacity. The actual infiltration rate equals the infiltration capacity only when the supply rate, rainfall intensity, less rate of retention equals or exceeds. Infiltration capacity depends on many factors such as the soil type, moisture content, organic matter, vegetative cover, season, air entrapment, formation of the soil seals or crust, etc. Of the soil characteristics affecting infiltration, non-capillary porosity is perhaps the most important. Porosity determines the storage capacity and also affect the resistance to flow. Thus, infiltration tend to increase with porosity. The vegetal cover increases infiltration as compared with barren soil because it retards the surface flow, giving the water additional time to enter the soil. The root system make the soil more pervious and the foliage shields of the soil from raindrops impact and reduce rain packaging of subsurface soils. As water infiltrates soil under natural conditions, the displacement of air is not complete even after many hours. Air spaces in the soil and the intermediate zone interfere with infiltration, as air is not pushed out by the infiltrating water but is gradually absorbed by the water. Due to this phenomena, infiltration rate may start rising towards a new high after a few days of continuous application of water. Surface conditions have a marked effect on the infiltration process and the formation of subsurface seals or crust, which forms under the influence of external forces such as raindrop impact and mechanical compaction, or through staking reduces the rate of infiltration. So, infiltration of water through subsurface or the surface take place generally over small periods of time, and it is the process of redistribution of soil water that goes on for most of the time and therefore predominates. When rainfall seizes the water that is wetted during the infiltration process starts to drain with the soil being wetted lower down the profile. The soil water conditions during the distribution period are therefore those that primarily influence plant growth and agricultural husbandry, and that also provide the buffer action in hydrologic cycle and the soil water zones has on the transport of water from the soil surface to the groundwater aquifer. As such, infiltration is critically interlinked with the phenomena of water evolution in the Vaduz zone, which includes wetting front propagation. In order to know infiltration rates of soil, infiltration tests are carried out. Cylinder or flood infiltrometers are common type of instruments which measure the infiltration as the rate of water leaving the device. Map showing the infiltration rates of soils are prepared. These help in designing the suitable artificial recharge structures and also to assess the extent of recharge from these structures. Now, we will go into the hydrogeological studies. A correct understanding of hydrogeology of an area of prime importance in successful implementation of any artificial recharge scheme. A desirable first step is to synthesize the available data on hydrogeology from different agencies. The regional geological maps indicate the location of different geological strata, their geological age, sequence, boundaries, context of individual formations, and the structural expressions like strike, dip, fault, fold, flexures, intrusive bodies, etc. These maps also bring out correlation of topography and drainage to the geological context. The map providing the information on regional hydrogeological rock units, their groundwater potential and general pattern of groundwater flow and the chemical quality of water in different aquifers are necessary. Satellite imagery maps provides useful data on geomorphic units and lineaments which govern the occurrence and movement of groundwater. A detailed hydrogeological study beside the regional picture of hydrological setup available for previous studies is therefore imperative to know precisely the promising hydrogeological units for recharge and correctively decide on the location and type of structures to be constructed in field. The hydrogeological investigations required before implementation of artificial recharge scheme are like detailed hydrogeological mapping, and the purpose of the hydrogeological mapping is to present the following maps which facilitate the analysis of groundwater regime and its suitability to artificial recharge schemes. The maps are maps showing the hydrogeological units demarcated on the basis of their water bearing capabilities both at shallow and deeper levels. The maps showing groundwater contours to determine the form of the water table and the hydrological connections of groundwater with rivers, canals, etc. And the map showing the depth of water table are usually compiled for the periods of the maximum, minimum and mean annual position of water table. Maps that show amplitude of groundwater level, fluctuations and the maximum position of water table of considerable importance for artificial recharge studies. Maps showing the piezometric head in deeper aquifers and their variation with time. Maps showing groundwater potential of different hydrogeological units and the level of groundwater development. The maps showing chemical quality of groundwater in different aquifers. The usefulness of all the above interpretive maps is additive, that is, their conjugative usage allow greater knowledge and understanding of an area than when a map is used separately. At this level of hydrological mapping of an area, few questions should be answered. Whether there is any gap in the data of subsurface geology of the available lithologs of any boreholes in the area are sufficient to arrive at a correct picture of aquifer geometry of the area. Whether the available data on the aquifer parameters is sufficient in case the area shows promise for artificial recharge techniques for deeper aquifers through injection wells, etc. Can the available groundwater structure serve the purpose of monitoring and effect of artificial recharge project? Now we discuss about the aquifer geometry also. The data on the subsurface hydrological units, their thickness and depth of occurrence, and to bring out the deposition and hydraulic properties of unconfined, semi-confined and confined aquifers in the area. The main stress is on knowing whether the subsurface rock types are sufficiently permeable or not to maintain high rate of infiltration during the artificial recharge. So, when it comes to the geophysical studies, the main purpose of applying geophysical methods for the section of appropriate site for artificial recharge studies is mostly to help and assess the unknown subsurface hydrogeological conditions economically, adequately and unambiguously. Generally, the prime task is to complement the exploratory program. Mostly it is employed to narrow down the target zone, pinpoint the probable site for artificial recharge structure and its proper design. Nevertheless, the application of geophysical methods is to bring out a comparative picture of the subsurface lithoenvironment, surface manifestation of the such structure and correlate them with the hydrogeological setting. Besides defining the subsurface structure and lithology, it can identify the brackish or the fresh groundwater interface, contaminated zone and the area prone to seawater intrusion. Using certain common geophysical methods, it is possible to model the stratification of aquifer system and spatial variability of hydraulic conductivity of the characteristic zone suitable for artificial recharge. Negative or non-productive zones of low hydraulic conductivity in unsaturated and saturated zones. Vertical hydraulic conductivity discontinuities such as dike and fault zone, moisture movement and infiltration capacity of the unsaturated zone, direction of groundwater flow under natural or artificial recharge process, salinity ingress, 10 and short denudation, depth salinity changes in the aquifers due to varied abstraction or recharge. The application of proper techniques, plan of survey and suitable instruments will definitely yield better understandable results, but of indirect nature. And now we will discuss about the chemical quality of source water. Problem which arises as a result of recharge to groundwater are mainly related to the quality of the raw waters that are available for recharge and which are generally require some sort of treatment before being used in recharge installations. They are also related to the changes in the soil or the soil structure and the biological phenomena which take place when the infiltration begins, to the changes brought to the environmental conditions. The chemical and the bacteriological analysis of source water besides that of groundwater is therefore essential. Suspended matter may clog the soil in two different ways. Suspended soils and a clogging problem. A major requirement for waters that are to be used in recharge projects is that they be silt free. Silt may be defined as the content of undissolved solid matter, usually measured in milligram per liter, which settles in stagnant water with velocities which do not exceed 0.1 meter per hour. To obtain still clearer water with only 10 to 12 milligram per liter suspended soils, further addition of flocculants and frequently agitation of the water must be restored. First, near the surface, the interstices of soil may be filled up and a layer of mud may be deposited on the surface. On the other hand, suspended particles may penetrate deeper into the soil and accumulate there. So, methods to minimize the clogging effect by suspended matter can be again classified into different groups. Periodical removing of the mud cake or dicing or scraping of the surface layer, installation of filter on the surface, the permeability which is lower than that of the natural strata, addition of organic matter or chemicals to the uppermost layer, cultivation of certain plant covers, notably certain kind of grass, providing inverted filter consisting of fine sand cores or coarse sand and gravel at the bottom of infiltration pits. Trenches are very effective. Clogging by biological activity depends on the mineralogical and organic composition of the water and basin floor and upon the grain size and the permeability of the floor. The only feasible method of treatment developed so far consists in thoroughly drying the groundwater in the basin and the assessment of subsurface potential for groundwater recharge. So, based on the hydrological and geophysical surveys, the thickness of potential unsaturated zone for recharge should be worked out to assess the potential for artificial recharge in terms of volume of water which can be accommodated in the zone, like source water availability, the studies should bring out the potential of unsaturated zone in terms of total volume which can be recharged.